This session is based on the question, the very question that what is quantum physics. So we have our session chair, Dr. D.P. Duwari. Am I right? Huh. So actually, right now when I came to know about Professor Duwari, when I was just discussing with him, right now he said that you don't have to tell many things about him. And honestly speaking, if I will speak everything about him, it will take, I think, half of the session. It's a big list of his achievements. I will just briefly tell him about him that Professor Duwari has done his PhD from Inter-University Center for Astronomy and Astrophysics from Pune, and he has been guided by Honorable Professor Jayant Vishnu Narlikar. So we should have give a big round of applause to his professor also. Professor Duwari is right now director with in research and academics, MP Birla Institute of Fundamental Research. He has been affiliated with many national and international institutions like University of Manchester, UK, Institute of Advanced Studies in Basic Science, Iran, and Tata Institute of Fundamental Research, India. You have received many prestigious awards. There's a big list. I'm unable to read all those numbers of awards. And you have attended almost 27 countries to deliver the different his talks and lectures in different conferences. And this is the list of the lectures. It is nearly 1200. So may I request to Professor Duwari to please take the charge of this session, and please give him a big round of applause.
A very good afternoon to you all. It's an immense honor for me and a privilege to be here today. And at least at the first session, just like the students sitting mostly at the back, I'm also a student today to learn about this beautiful aspect of quantum physics and consciousness from brilliant minds, erudite speakers, and the leaders of our society, of not only in terms of other social activities, but also academics and our understanding. I think human perception of anything which is either subjective or objective, any material, metaphysical, or spiritual concepts, it is just not a singular input from the environment. It is rather a result of layers of experiment, of different understanding, different feelings, different realization and concepts. So, any conscious thought, any consciousness about any object, any event, it is basically not a singular thing. It is addition, superposition of lot of states, which is also, I think, the hallmark of quantum physics. The non-deterministic property of both consciousness and quantum physics that makes them tremendously interesting, challenging, and obviously young minds should get involved into it. And to do that, to introduce the subject itself of what do we mean by quantum physics, quantum mechanics, or quantum world, or quantum consciousness, I think the best way to do is by two experts who are going to give lecture in this first session. Professor Partho Ghosh, he is really one of the most brilliant minds in this particular arena of human knowledge, and obviously Professor G.P. Dash. So each talk is structured around 40 to 45 minutes of deliberations. And after that, though in the schedule that you have got, there is question and answer session after every speaker, but we discussed and decided that let both the speakers first give their deliberations, and only at the end of both their deliberations, we'll have a joint question answer session. So without lengthening the whole process of telling what it is and what it is for, let us hear the brilliant talks of Professor Partho Ghosh and Professor G.P. Dash. It is also an opportunity for me, an honor for me to introduce these two brilliant minds. Professor Partho Ghosh, Senior Scientist, Platinum Jubilee Fellow of National Academy of Sciences, India, Center for Astroparticle Physics and Space Sciences, Bose Institute, Calcutta. Professor and Academic Program Coordinator, retired, of S.N. Bose National Center for Basic Sciences, Kolkata. Earlier, he was Science Officer, British Council, Kolkata, and prior to that, Adhyapak in Physics, Vishwabharati, Shantiniketan. He is one of those rare personalities amongst us who was a student of Professor Satyendranath Bose, Nobel Laureate and FRS, and Professor Abdul Salam, Nobel Laureate. Satyendranath Bose, FRS, sorry. Dr. Partho Ghosh has many publications in international journals and is internationally acclaimed for his contribution to quantum mechanics. He is a regular referee to the Physics Letters A, which is Europe's leading physics journal, and the Foundations of Physics, and the author of highly acclaimed books such as Testing Quantum Mechanics on New Ground, published by Cambridge University Press, Riddles in Your Teacup, published by Indian Institute of Physics, UK, which has been translated into quantum into everyone for young kids and everyone around. In addition to that, my personal introduction and experience of Professor Partho Ghosh is really something. I still remember he's one of the founding, not fathers I will say, but founding faculty members of this S.N. Bose Center. When it was run from a 3-storied building without its present big splash campus, he was the person who initiated, who helped and catalyzed the growth of this fantastic institute that we have today. I also remember the person, generations of young students have got motivated by him, seeing his program in the television, in the national television, when he spoke about science, application of science, and the magic of science to the young minds. So in addition to this very heavy stuff of quantum mechanics, quantum consciousness, and others, he's a person who has touched almost all scientific-minded hearts. I welcome Professor Partho Ghosh.
Good afternoon, everyone. I would like to begin by thanking the organizers for giving me this opportunity to be at this very unique conference. My task has been made very simple in the sense that instead of talking about the interface of quantum physics with consciousness, I will just talk about quantum physics. Because unless one has a very clear idea of what quantum physics is all about, it will be very difficult to make any connections if there is any. So I will start by telling you how quantum theory came to be, the initial stages of quantum theory, and in particular, the great contribution made by Professor Satyendranath Bose, and how that catalyzed the further development of quantum physics. So it all starts in the latter half of the 19th century when people were studying what is called black body radiation. Now, what is a black body? A black body is a body which absorbs all the energy that is incident on that body. So that's why it looks black. Now, if you have, when you heat a body, first it gives you some, if you are near it, you can feel the warmth. So there's some radiation which is in the infrared, which impacts on our senses, and all we can feel is the warmth. We don't see any changes. Then gradually the thing becomes red hot. And then if you keep increasing the temperature, it finally becomes white hot. When you know that white consists of all the 7 colors, the Vibgyor, so it's emitting all the colors. And scientists wanted to find out that when a black body is in equilibrium with its surroundings, how does the spectrum of that radiation look like? In other words, as I said, at every temperature, let me show you these graphs which were actually plotted by experimentalists. Anyway, you see the red curve at the bottom. And what is being plotted here is the energy on this axis and the wavelength on the other axis. The wavelength means the crest to crest or trough to trough distance in a wave. Now we all know, or at least we knew, that radiation consists of waves, so they have wavelengths. So all sorts of wavelengths are actually emitted, but a particular one dominates, and that the red curve shows that that is the state where the red color dominates over all the other colors. But if you keep increasing the temperature, then that shifts to the left, that is towards lower wavelengths, when it becomes green, further left when it becomes blue, and so on. So these are the actual curves which the experimentalists plotted. But then there was a problem. The problem is the following, that towards the extreme left is the region of ultraviolet. Now, classical wave theory says that infinite amount of energy should be emitted from that region. You see that curve on the right, which is called the classical theory. So it keeps on increasing and increasing and increasing. So a body which is highly heated would emit infinite amount of energy, but that is of course impossible. So right from the beginning, there's something wrong in the classical theory. However, the actually observed curves do not go to infinity. They turn down as you go towards the ultraviolet. So this so-called ultraviolet catastrophe is actually not there in nature. The curves turn down, and there's some mechanism which cuts off the energy that comes from the ultraviolet region. So the problem was, then what to do? Classical theory says infinite energy should come out. Empirically, I see that that does not happen. Any reasonable person would also say that shouldn't happen. But then, what to do with this situation? How to even describe these curves mathematically? So that step was taken by Max Planck, Germany, sometime in December, or rather towards the end of the year 1899. And by a fit of inspiration, he just wrote down a formula which exactly describes those curves. And this is that famous formula. On the right-hand side, you see two factors, 8 pi nu square over c cube. Don't worry about this, what they are. And then there is a second factor in which there is a constant h, which is nowadays called Planck's constant, that appears in physics for the first time. The first factor is what you get from classical theory. The second factor you do not get from classical theory. That is the factor which Max Planck just wrote down to fit the curves. But then the question arose, what is the kind of physics which should give rise to that second factor? And it is at this stage that Planck proposed that when a black body absorbs or emits energy, it doesn't do so continuously, but in some packets. So let me try and explain that in terms of a very simple image. Think of a high-rise building. Now, if you want to throw a ball to the first floor, then you have to give it a certain minimum amount of energy, otherwise it will not reach it. If you want to send it to the second floor, you have to give twice that amount of energy. The third floor, thrice that amount of energy, and so on. But now think of the reverse process. Supposing you are throwing a ball from the fifth floor to the ground, then it will emit, then when it comes down, there is a change in energy which is 5 times that basic unit. Now, this basic unit of energy is called the quantum of energy. Of course, it doesn't apply to actual high-rise buildings. This is just a pictorial representation. But this is exactly the kind of model which Planck had in mind, which is called the harmonic oscillator, which is with equally spaced states. But then came Albert Einstein in 1905. You see, Planck had only said that the process of emission and absorption is quantized. But the radiation itself is not quantized in Planck's theory. But Einstein said that that cannot be true. He did a very simple statistical analysis of the Planck law, and he concluded from it that the radiation itself must also have a kind of particle-like structure, which at that time he called the light quanta. Quanta of light. Light itself propagates as little packets of energy. I'll show you a little video here. Can somebody help me? Which will give you a pictorial representation, very rough one, of what Einstein meant. But you mustn't take this too seriously. First of all, photons go very fast. They can go 7.5 times around the Earth in a second. But what you will see are slowly moving photons. So everything has been speeded down to a great extent. So that light video. Yeah. Can you show this? Yeah, you can see that there's a light, but also little particles inside the light which are falling. So this is a very rough physical idea of the photons. So let's go get back. Okay. So light travels both as waves as well as particles. So this was the beginning of what is called wave-particle duality. Something that we knew was a wave suddenly acquires also a particle character. Okay. With the help of this idea, Einstein was able to explain something which could not be explained again by classical theory, which is the photoelectric effect. When light falls on a metal, then usually electrons are immediately emitted. Immediately, that's an important point. Immediately emitted. But there are certain characteristics of photoelectricity. One is that there is a certain energy threshold. That is, all light will not be able to have this effect on all metals. There's a certain minimum amount of energy which this light must have for that particular metal to be able to eject the electrons. The number, but not the energy, of the emitted electrons increases with the brightness of light. If you make the light brighter and brighter, you will get more and more electrons coming out, but their energy will not increase. Their number will increase. And the energy of the emitted electrons will increase if you make the light more blue, bluer and bluer. Then you will have, but in that case, with a constant illumination, the number will not change, but the energy will change. Now, these features of photoelectricity could not be explained by any classical wave theory. Einstein showed in a very simple way that if the photons in the light will come and hit the electrons inside the metal and kick them out instantaneously, and he came up with a very simple mathematical expression for it, which was verified. And he got the Nobel Prize actually for this work. But for a long time, people doubted it, including Max Planck himself, that light just could not be dual. We know it is a wave. So, the objection was that we know waves spread. And when the two waves spread, when they meet, they interfere to produce certain patterns that you can see, even in water waves. But particles are not spread out. They are located at points, and they do not interfere. So, what is happening? So, this is the great problem of wave-particle duality, which was first talked about by Einstein. And this duality has been shown to be true for every particle. That's a later on story. Now, so Einstein's photons, what he had in mind are point-like entities traveling like a swarm of tiny bullets, independent of one another, just like bullets would do, or cricket balls would do, or billiard balls would do. But some people immediately pointed out, including Professor Ehrenfest, that itself would contradict the Planck's law. And Einstein had to agree that would. So there was a big problem. Einstein was flabbergasted. He drew a conclusion from Planck's law, and now that there should be photons, and now people are telling me that these photons, if they exist, would contradict Planck's law. See, this was a big problem. Then came in 1913 Niels Bohr with his model of the atom. I don't need to go deeply into it, but I think you all know that the electrons in atoms come in orbits. And when they are in that orbit, they do not radiate. That is a fiat, Bohr's fiat. They are called stationary states. If they are in those states, they don't radiate. But if they jump from one state to another, then the excess of energy is radiated as light. And this idea worked very well and revolutionized physics. Einstein was very happy with it. He says this is the highest form of musicality in the sphere of thought. Then in 1923 came another discovery by Compton, where he was scattering X-rays of objects, and he found that the incident X-ray hits the electron and goes off as another X-ray, but with lesser energy in it, that is, larger wavelength. And the electron which is hit recoils exactly as would happen if a billiard ball came and struck another billiard ball which is stationary. Then the stationary ball would recoil and this ball would go off in another direction. So this was a direct proof that X-rays, which is electromagnetic radiation, behaves like particles, just as Einstein had guessed. So the story is developing. The corpuscular idea is gaining ground. But obviously, it is in contradiction with the wave nature, as also with Planck's law itself. This was the state of physics. So there arose the need for a satisfactory theoretical understanding of Planck's law, what is called a derivation of Planck's law from basic axioms. And the first person to do that was Planck himself. Then came Peter Debye in 1910. Then came Albert Einstein in 1916 with a wonderful paper which forms the basis of what we call lasers today. Then Pauli in 1923, and then Ehrenfest and Einstein in 1923. All of them gave different derivations of Planck's law. Now, this was the state of physics when Professor Satyendranath Bose was teaching quantum physics in the University of Dhaka. And he told me that he was finding it very difficult to explain to his students the basic ideas because they were all confused. I mean, the whole of physics was in a very confusing state. It was not clear at all. So then he thought that he must give a satisfactory derivation of this law himself. So if you look at the Planck's law again, as I told you, there are two factors. The first factor everybody took from classical theory and gave some kind of arguments to get the second factor from quantum theory. Now, Bose said this is very illogical because you're using both classical theory and quantum theory at the same time. This is hodgepodge. This won't do. We have to have a derivation of the whole formula from quantum theory. Don't use any classical ideas at all. And he came up with such a derivation in which he assumed the following thing. Now, I have to be a little technical here. There's something called phase space in physics, which is 6-dimensional. It's very simple, actually. This space is 3-dimensional. This is ordinary space, right? Now, every particle has also a momentum. So the momentum is a vector which also has 3 components. So if you add that, so if we are thinking of a moving particle, then actually it exists in a 6-dimensional space, mathematically. So that is called a phase space. Now, Bose assumed that phase space of electromagnetism was not a continuum, but it was broken up into little cells of volume Planck's constant h cubed. Then it becomes granular. Now, once it becomes granular, then you have to say, okay, there are so many sort of boxes or pixels or whatever you call it. Now, how many photons can I put in each? You can have no photons, you can have 1, 2, 3, etc. There's no limitation on how many photons you can put into one. However, once you have put all the photons into one, then because that is something which is fundamentally a unit, you cannot then go and say that I will interchange the balls and get new, the photons and get new arrangements. That you cannot do. So that means he is now introducing a new statistics where the interchange of the photons will not give you a new arrangement. This is not true of anything classical that we do. And that immediately gave him Planck's law. Not only the first factor, the second factor, everything came out. So he sent his paper to Albert Einstein. He first of all sent it to Philosophical Magazine. They rejected it. Then he sent it to Albert Einstein with a letter. And Einstein was so delighted because he suddenly saw that his basic intuition of photons is correct, except that it's not a point-like particle. It's somewhat smudged. In other words, the particle nature and the wave nature are integrated in some way, which therefore requires a new way of counting and new statistics, and that these photons do not travel independently of one another. There is a mysterious correlation. People asked Einstein, what is this mysterious correlation that you and Bose are talking about? This just doesn't make any sense. So Einstein said, you're right, it doesn't make any sense, but this is the only way to count, which give you Planck's law, as well as something called the Nernst heat theorem, which no other way of counting will ever give you. So this is right. Let's accept that there is something mysterious going on. We will learn it later on. It's too early for us to bother about it. Let's carry on with the development. So what Einstein, being Einstein, he immediately applied Bose's way of counting to material particles. Particles, the constituents of gases. And then when he did it, he found that those particles of gas should have a wave-like character. So now the story is turning. So whatever was thought to be a particle is now turning out to be also having some wave characteristic. Now he remembered that about a year before this, somebody from France called Louis de Broglie had sent him a thesis in which he had actually proposed that if light has, which is a wave, has a particle character, then particles should also have a wave character. Einstein thought it was too speculative, and he did not respond at all. So Louis de Broglie was waiting for Einstein's approval of his thesis, which wasn't coming. Then when Bose's paper came and he saw this, he immediately wrote to de Broglie's teacher, who was Einstein's friend, Paul Langevin. And Langevin said, can you send me a second copy of that thesis, which was done? And that is when Einstein started writing about Bose and about de Broglie. And he himself said that experiments should be done with material particles to see whether they diffract like waves. Now, accidentally, matter waves were discovered soon afterwards by Davison and Germer. They were scattering electrons from crystals, and they saw this peculiar feature that the electrons going through crystals are behaving like waves. You're producing patterns as if they were waves. So they got the Nobel Prize. So this is the kind of pattern which electrons produce while going through crystals. So the question came, what is the equation of motion of these matter waves? They're waves, but what is the equation of motion? So this was ripe in the physics circle, and the person who came up with the equation that describes these waves was Erwin Schrödinger. So he wrote down his famous equation, which forms the basis of what we call quantum mechanics today. And you will hear more about it from Professor Das. Now, there is Walter Moore has written a biography of Schrödinger. It's called Schrödinger, Life and Thoughts. If you look at page 188, you will see that he quotes Schrödinger as saying, wave mechanics was born in statistics. The story is that Schrödinger thought that Bose's counting is just wrong. And he wrote a letter to Einstein saying why it is wrong. Einstein sent him a postcard, which is there in this book, where he drew little diagrams to show why Schrödinger was wrong. And Schrödinger completely changed. And then he came up with this equation. So this is the history of how quantum mechanics was actually born and what role our great S.N. Bose had to play in this. Being a student of Bose, I cannot help highlighting his contribution. And this is also for our younger students because they should feel inspired. This kind of idea in 1924, sitting in Dhaka, it's absolutely amazing. And now I'll just tell you what follows from Bose's statistics. Now we know today that there's another form of statistics called the Fermi-Dirac statistics. I'll not go into the details, but let me tell you that everything that we know of today, absolutely everything, is either a boson or a fermion. There cannot be anything else. All fundamental particles are either fermions or bosons. Now, to explain it to common people, I usually say that when a child is born, you usually ask, is it a boy or a girl? So whenever you discover a particle in an experiment or you theorize the existence of a particle, you have to state or find out whether it's a boson or a fermion, because there can't be anything else. So 50% of anything that exists are bosons. Like photons, pions, kaons, the W's, Z's, helium-4 atoms, and so on. And fermions are things like protons, neutrons, quarks, electrons, muons. Now, in 1925, Einstein predicted that if Bose's statistics is correct, or if it is correct to apply Bose's statistics to material atoms, gases, then at very, very low temperatures, below a certain critical temperature, all the particles should go down to a lowest energy state. So here you have the energy and the number of particles in each level, each quantum state. As you cool the thing, the particles from the top start coming down to the lower states, and finally, near absolute zero, they all come down to the ground state. That is called a Bose-Einstein condensate. It took 70 years to discover Bose-Einstein condensates in the lab, and the people who did it are Cornell, Wieman, and Ketterle, and they won the 2001 Nobel Prize for this discovery. Also, there are things called superfluidity. I'll show you something, a rather nice video. So I will not spend more time on that. And Lev Landau came up with a theory of why there is superfluidity in helium-4. And he showed basically that helium-4 atoms make a transition to Bose-Einstein condensates below a critical temperature. And Bose-Einstein condensates have this character that the liquid loses all viscosity. So it flows through even the smallest imaginable pipes, or whatever you call it. And he got the Nobel Prize in 1962 for showing that superfluid helium is a consequence of Bose's statistics. Lee, Osheroff, and Richardson won the 1996 Nobel Prize for discovering that liquid helium-3, which is a fermion, becomes superfluid, but at much lower temperatures. So this was a problem, and the person who solved that problem is Anthony Leggett, who won the 2003 Nobel Prize for showing how the fermions in the superfluid pair up to form bosons and then condense to give you superfluidity. There's another phenomenon called superconductivity. Below a very low critical temperature, certain metals become superconductors. That is, they lose all their electrical resistance. This is a wonderful property. And you can have magnetic levitation because of that. I'll show you a video for that. Bardeen, Cooper, and Schrieffer won the 1972 Nobel Prize for their theory of superconductivity, which is based on the fact, actually based on Bose's work, but what they did is the following. The electrons in metals are fermions. So how do they condense? They can't. So they showed that at very low temperatures, because of their interaction with the lattice, they form pairs. They're called Cooper pairs. Pairs of electrons with opposite momenta. They become bosons, and then at certain low temperatures, they can condense into the lowest state and flow without any resistance. Again, Bose's work, getting a Nobel Prize in 1972. Finally, of course, we know about the Higgs boson and the God particle and so on and so forth. Again, it was in the 1960s when the new, the standard model of particle physics was just being developed. There was a problem. The problem was the theory said that all the particles must be massless to preserve a certain symmetry. Now, massless particles must fly off with the speed of light. If that is so, then how do they form matter, solid matter? So there was a need for a particle which will give mass to all the other particles. And that particle, Higgs and many others, incidentally, I don't know why their names are never mentioned, the Higgs showed that if there is a boson, then it can do that trick. The new boson came to be known as Higgs boson, and this was, of course, discovered, and Higgs, as well as another gentleman who had proposed the same theory, Englert, they won the 2013 Nobel Prize. So you see how many Nobel Prizes have been given on the idea, simple idea which Bose gave in 1924 from Dhaka. But unfortunately, Bose was never given a Nobel Prize. So we asked a lot of people, physicists, to mention the names of the 10 Nobel laureates of the last 10 years. Nobody ever succeeded. Is there anybody here, physicists, who can mention the name of 10 Nobel laureates in the last 10 years? I bet you cannot. But is there a physicist here who has not heard of Bose? No. You cannot do physics without Bose. So who cares whether he gets a Nobel Prize? Anyway, so I think I've stopped my presentation. I'll just show you 2 short videos. See, there's a magnet there on the right, that one, and there's something that can be made into a superconductor by pouring liquid helium. So as you pour that liquid helium, that becomes a superconductor. And if you bring the magnet over it, it levitates. Because there's something called the Meissner effect. The magnetic flux lines cannot enter a superconductor, so it repels it. So this is, again, a consequence of Bose's statistics. Can you imagine? A simple idea can have such wonderful physical effects. Now, as this thing warms up, you will see that it will drop, because once it is above the critical temperature, it's no longer a superconductor. It becomes an ordinary conductor, and this effect disappears. Wonderful, isn't it? Now, there's no way of understanding this without my guru, S.N. Bose. I feel so proud about it that I had the great opportunity to have known him. I feel blessed. Now, next one, the final one. Superfluidity. This has audio in it, so you should hear the audio. Audio. Where's the audio?
Until at 2 degrees above absolute zero, a dramatic transformation takes place.
We'll start it again.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
And that new theory is, of course, Bose's way of counting. Thank you very much.
Wow, what a journey. It was a fantastic journey through the historical developments and evolution of this beautiful and wonderful, exciting subject of quantum physics, quantum mechanics. And also it reminded us that we are so fortunate that we have the opportunity of celebrating one of the best minds in scientific world that was there, Professor Satyendranath Bose. And I also felt a pang of pity for those who couldn't have the opportunity of celebrating this scientist, whatever. The next speaker, Professor G.P. Das of Indian Association of Cultivation of Science, will be speaking on the quantum world revisited. Professor Das, Gaur P. Das, is a condensed matter physicist working as a senior professor in the Indian Association for the Cultivation of Science in Kolkata. His research interests span a wide cross-section of encompassing electronic structure and properties of various kinds of alloys, interfaces, clusters, and nanostructured materials. More recently, he has been working on hydrogen storage and spintronics materials. After graduating from Calcutta University, he had obtained his PhD in physics from Bombay University. He did his postdoctoral research in the Max Planck Institute for Solid State Research in Stuttgart. He served as a visiting scientist in several institutes abroad, such as Max Planck Institute, Stuttgart, Germany, Virginia Commonwealth University, Richmond, USA, Institute of Material Research, Sendai, Japan, and University of New South Wales, Australia. He is a recipient of the Materials Research Society of India Silver Jubilee Award and is a member of the West Bengal Academy of Science and Technology. Professor Das has authored and co-authored a large number of research papers as well as review articles in international journals and has also written several book chapters. He has spearheaded a number of national and international research programs such as the Asian Consortium for Computational Material Science, Asian Hydrogen Storage Initiative, of which is a coordinated research program on spintronics materials, etc. He is well known for his popular level scientific lectures delivered in various forums. He is serving as a distinguished visiting professor in several institutes and is also a mentor of the INSPIRE program of the Department of Science and Technology. Ladies and gentlemen and students, let us welcome Professor G.P. Das.
Well, thank you very much, Mr. Chairman, for your nice introduction. And let me start by thanking the organizers. Well, I don't need this. Let me start by thanking the organizers, in particular Professor Sudipto Ghosh, for inviting me to this very nice and unique conference. And I must confess that this is the first time I'm organizing, I'm attending a conference like this, you know. So I am speaking to you with a little bit of awe because, you know, I know that there are people here in the audience, you know, who are absolute stalwarts. I don't need this. Yeah, absolute stalwarts in this field. And so, no, you know, because I take lectures for 500 students, so I can easily, a very loud mouth. My wife says that. So anyway, after such a wonderful lecture by Professor Ghosh, that has, of course, made my situation a little bit better. So what I'm going to do is the following. I'm going to tell you in as non-mathematical way and as simple way as possible something about the quantum world. And I know that here in the audience I can see that if I leave aside some of the stalwarts sitting in the front, I can see some of the youngsters here in the audience, and some of them may already have got some background of quantum physics and some of them may not have. So with that premises in my mind, I would like to start my lecture, and a little bit of a apology for those who are experts in this field. Okay, so I'm coming from this institute, which is Indian Association for the Cultivation of Science, and this institute, most of you know that this institute is famous because this is the place where Sir C.V. Raman, another stalwart of Indian science, after Professor S.N. Bose, which Professor Ghosh already told you, you know, he did his work on Raman effect that from this institute, and that's the one which bagged him the Nobel Prize for the discovery of Raman effect, and here is the plaque for the Raman effect. Okay, now. Now the plan of my talk is the following. I'll start with some introductory remarks on quantum revolution, then I'll come to the postulates of quantum mechanics, okay? Very simple way, as simple as possible, I'll try to do that. And then I'll come to EPR paradox, what it is, you'll come to know, and the Bell's inequality. The formalism and logical foundation of quantum mechanics is something which takes a lot of time, but I'll just touch upon something which I feel is essential for this audience. Various interpretations of quantum mechanics. Now this is something where you know, things start becoming really difficult, complicated, and so on, but I'll try my level best to see what I can tell you in as a layman's word, the interpretations of quantum mechanics, and I'll conclude with some thoughts on causality and consciousness. But of course, since I have come here to learn things on the relationship of consciousness with quantum physics, so definitely I am not the one to whom you have to look for consciousness, because there is a huge number of lectures that you will be seeing after that. Okay. Now you see, I am coming from an institute where there are departments of physics, chemistry, and biology. Okay. Now physics, according to me, is something which is related to originality. Chemistry is something which is intimately linked to diversity, and biology is linked with complexity. And all the three together is coming to reality, which is called life and nature. So that is why, you know, we talk about physics, chemistry, and biology. Now the laws of nature is something which is very, very simple if to start with, because you see the gravitation, for example, you know, I mean, sorry, what did See, gravitation, sorry, where is the, oh, yeah, okay. This one, but it's not coming. Oh, you can't see that. Okay, fine, doesn't matter. So you see, the laws of nature, two laws of nature, most of the people we are experiencing. One is the gravitation and the other is electric field. Now you see, in gravitation, you see the gravitational force is G into m1 m2 by r, divided by r square. If there are two masses, let's say one say moon and the earth, or the earth and the sun, they are attracted to each other, and the masses are m1 and m2, and the distance between the two is r, so there is the inverse square law. Look at the other one, the electric field. If there is a charge here and a charge here, whether it is positive or negative, it doesn't matter. The Q1 and Q2 are the two charges, and there is a force between them which is also inverse square. So you see, both gravitation as well as electric field, both of them are inverse square law. But of course, if you calculate it, I mean, if there is a student of physics or chemistry here, he can easily calculate this, these two, because we know the value of G, the value of K, Q1, Q2 and M1, M2. If I give you, let's say, an electron and a proton, calculate that. You will see that between an electron and a proton, the Fg and Fe, if you calculate, you will find that the Fe is 40 orders of magnitude more than Fg. That means you can as well neglect a gravitation if you want to consider the subatomic particles that Professor Ghosh mentioned. However, if you go to celestial objects, with which our the chairman is the one who is one of the one of the authorities on celestial objects, he will say that no, it is the first one which is much more important for that. So depends on what are you talking about. Are you talking about cosmos or are you talking about subatomic particles? Now, this is something which I was reading this book, The Grand Cube of Theoretical Physics. I got from this book which is known as, which I read recently. It is Sleeping Beauties in Theoretical Physics by Thanu Padmanabhan, who is in IUCAA. Okay? Now this book is an absolutely amazingly written book, Sleeping Beauties of Theoretical Physics. And here what he did is that the entire physics he wrote, he tried to picturize in terms of the three axes. The x-axis is, this x-axis is h, Planck's constant. The y-axis is c, velocity of light, and the z-axis is g, the gravitational constant. Now all these three are constants, g, h and c. It does not matter where you are, whether you are in America or Canada or India. I mean, these three things are absolute constants. And in terms of these three constants, you can describe classical mechanics, quantum mechanics, relativity, special relativity, general relativity, quantum gravity, and even if some of you have read what is called theory of everything. So you can really discuss everything in terms of these three axes. This is called the grand cube of theoretical physics. So if you want to go from classical to relativistic, you have to tune with the c, the velocity. If you want to go from classical to quantum, you have to go in the h axis. So depending on in which axis you are going, you can generalize from our standard conventional Newtonian classical mechanics to the quantum or to relativistic. Now the period 1, that is a quantum revolution, which Professor Ghosh has already told you very nicely. We are aware that the classical mechanics reigned as the dominant theory of mechanics for centuries. Nobody questioned them. I mean, whether it is Newton's laws or Lagrange's or Hamiltonian mechanics, or the most famous treatise by Maxwell in the 19th century, okay, and followed by Faraday, which in fact formulated the entire thing about electricity and magnetism that we know of today. And then came Boltzmann's entropy equation. All these things were before the 20th century. But in quantum mechanics, which, as Professor Ghosh already told you, started with the Planck's black body, and he already mentioned, in fact, all these things, whatever I told you, Planck's black body, then Einstein's photoelectric, then Bohr's model of atom, de Broglie's wave particle duality, Of course, then he did not get time to talk about Pauli's exclusion principle, Heisenberg's uncertainty principle, Schrödinger equation, and finally Feynman's path integral. Now these are some of the things, some of the landmarks. And if those of you who are interested, in fact when I was very young, I read the book 30 Years That Shook Physics by George Gamow, okay? An absolutely beautiful book as to the first 3 decades of 20th century, how important it was for the quantum theory. It's written in that book. Now look at this. These are the, I'm sorry, there is some problem with the thing, and I'll just tell you. So these are 4 remarkably simple relations. One is by Planck, E equal to h nu. The nu has not come out correctly here. H nu is the frequency. De Broglie, that is lambda equal to h by p. Heisenberg's, that is delta x into delta px is greater than equal to h slash, and Einstein's E equal to mc square, which all of you know. Now these 4 relationships are so remarkably simple, and that completely shook the foundation of what we call it a classical world. Now again, I don't want to go into that, because right from 1900 to 1950, there were so many stalwarts, starting from Max Planck, Einstein, Niels Bohr, Rutherford, de Broglie, and then Heisenberg, Schrödinger, Pauli, and so on. Okay, this is the history of quantum mechanics in the first half of 20th century. These are all available in the literature, and very nicely written and exciting, absolutely, I must say that. This is a very important picture which you will find in many places. That is the first Solvay conference, where Albert Einstein was the youngest, while Louis de Broglie, as he said, Louis de Broglie is not even there, because he was a kid at that time. The next Solvay, afterward, the 5th Solvay conference is something which is again a very important conference, where they discussed about the foundation of quantum mechanics. Now the quantum mechanics, its triumph or mystery or both. Now that its triumph because of its towering mathematical structure and amazing empirical accuracy. It's towering. Mystery because of the conundrums about how to interpret it, and that's exactly why I think this kind of a conference is very important, because the interpretations of the quantum mechanics is something where the shoe starts pinching, and I will try to in my very poor and humble way, I'll try to share with you some things which at least I have understood. Now Richard Feynman's famous saying that I think I can safely say that no one understands quantum mechanics. That's what Richard Feynman said, of course, from his point of view. Now the laws of quantum mechanics are founded upon several fundamental postulates. So I'll just tell you first, I'll start with that, the postulates of quantum mechanics. What are the postulates? The fundamental postulates are the following. Number 1, all information about a system is provided by the system's wave function. Already Professor Ghosh introduced the concept of wave function by Schrödinger. Okay? Now the postulate 1 is all information about a system is provided by the system's wave function. Postulate 2, the motion of a non-relativistic particle is governed by Schrödinger equation. I am particularly telling non-relativistic because later on it was Klein-Gordon and Dirac equation, which was a generalization of Schrödinger equation for particles which are moving with velocity close to the velocity of light, which is called relativistic. But for non-relativistic one, where the velocity of the electron or any other subatomic particle is something which is much lower than the velocity of light, you can safely use Schrödinger equation. This is postulate 2. Postulate 3 is the measurement of a system is associated with what is known as a Hermitian operator. You need not know, but Hermitian operator is something which corresponds to what is known as an observable. Because unless if you want to do an experiment in the laboratory, you have to have an observable, and the corresponding operator has to be Hermitian operator. Now these 3 are the fundamental postulates of quantum mechanics. And here I have tried to give you some kind of a pictorial form of the postulate 1, that is all information about the system is provided by the wave function. This is how the wave function will look like, and the wave function can be something which can be positive or negative or maybe complex valued. Okay, this is the left side. However, when you square the wave function, the squared amplitude of the wave function, this is called the probability. That means what is the probability that a particular subatomic particle is lying here or not. Now let me tell you, this is very important, because to a complete layman, let's say I am trying to tell it to a class 5 boy, classical versus quantum. I tell you, I call you, I give you a deuce ball and I tell you, you throw the deuce ball. Now if you throw the deuce ball, it will take a parabolic path and land somewhere. Now if I ask you to tell me what is the position x, comma, at a particular time t where the deuce ball is, you can tell me. It's very simple. It's very simple using Newtonian mechanics. You can tell me the deuce ball at a particular, depending on what strength you have thrown, with what velocity you have thrown, at what angle you have thrown, I can easily point out what is x comma t, that is the position comma time. At what time, what is the position of the deuce ball? It's very simple. Now, suppose I repeat the same experiment not with the deuce ball but with an electron, and I ask you, okay, throw the electron. Is it possible for you to give me x comma t? The answer is no. Why? Because Heisenberg told us that, look, it is not possible for us to determine the position and the momentum simultaneously. So the difference between a deuce ball and an electron is that deuce ball is a classical particle, electron is a quantum particle. So you can at most tell about what is the probability that the electron will be here or here and so on. I'll tell you more later. Then postulate 2, that is the non-relativistic particle is governed by Schrödinger equation. This is mathematics. Those of you who are not familiar with it, forget it. This is the time dependent and time independent Schrödinger equation, which is at the heart of most of the the conventional quantum mechanics that we are talking about, but it is not necessary. Next, third postulate is something which is the the operator, this thing. Again, we can skip this, not necessary. So quantum mechanics and the principle of superposition, it is I think one of the best ways it was done was by Dirac when he was taking a class for the students. So let's have a snapshot of a lecture taken by Paul Dirac that enthralled the students by the clarity and majestic unfolding of his argument. So what Dirac did is that he took a piece of chalk and broke it into two parts, and then what he did, he placed one fragment at one end of the table and another fragment at the other end of the table. So he said, Dirac said that classically what happened? Yeah. So what Dirac said is that classically there is a state where the piece of chalk is here or where the piece of chalk is there, and these are the only two possibilities. Now replace the chalk, however, by an electron, and the quantum world, in the quantum world there are not only states here and there, but also a whole lot of other states that are mixtures of this here and there. And this is in a very, very simple way, this is what is called, what is the beginning of the principle of superposition, okay, which is obeyed by the quantum particles. So there is a famous experiment which is called a double slit experiment. Why I am telling you is that this will be understandable even by a non-science student. Look at this. If suppose you are allowing the particles to go through a single slit, one slit, okay, and the particles that pass through the single slit produce an image on the detector, and if you see the image, it will be something like a Gaussian distribution, okay, very simple. But instead of that, suppose instead of one slit I have two slits, then what happens? I repeat the experiment with two slits. There are two slits now. If I do the experiment, what is expected? The expected is that, okay, there will be two Gaussians. Look, there are two Gaussians. One is here through this slit and the other is here. and the two superposition will be something like that, but that does not happen. It does not happen that way. This is not what you get, okay? This is wrong. What you get is something which is this, and this is called interference. Now, this interference is something which is the first thing which tells us, okay, there is a superposition of the thing. So that is a glaring example. Okay, so the quantum mechanical explanation is that each particle passes through both the slits and interferes with itself in order to give rise this kind of a superposed states. Okay. So the wave function of each particle is a probability wave which produces a probability interference pattern that passes through the two slits. So the superposition principle, you don't have to read it, the superposition principle implies the two very general features of quantum mechanics. One is that it is no longer possible to form a clear picture of what is happening in the course of the physical process. And secondly, the other consequence is, whatever I have written in the red, it is no longer possible to predict exactly what will happen when we make an observation. So you heard in the morning today that observer has a role to play. Okay? So this superposition principle has got a lot of ramification which we can discuss in some other forum. Another example I would like to give you, I cannot help but giving you. This is something which happened much later. This happened in the later part of 20th century in Bell Labs. You know what it is? You know, each of these are atoms. 1, 2, 3, 4, these are all atoms. These are all cobalt atoms which are placed on a copper substrate. How you can say, I mean, how can you see atoms? Yes, it is possible. There is something called deep pen lithography. Now, you don't have to know what it is, but I can explain to you. You know, not you people, but your parents or grandparents used to write with an ink pen. We don't write. We write with ball pen. Now, what do we do with ink pen? We dip it in the ink, take it out, write. Again, when it is dry, we dip it again. Here also we did the same thing in a much more sophisticated way, of course. What we do is that you dip it, take out an atom, put it. Again dip it, take out an atom and put it. It is called dip pen lithography. Using dip pen lithography, this thing has been produced. And now why am I showing you this picture is something which you will realize in the next one. There is something called scanning tunneling microscope. Now this scanning tunneling microscope is something which for the first time allowed us to see an atom. You can see an atom using scanning tunneling microscope. Don't ask me what is the principle, it is not necessary, for which the Nobel Prize was given in the mid-80s to Swiss physicists. But what I am going to show you is the following. The same coral that I showed you, okay, is here. And you know, so these are all cobalt atoms, and there is one atom here. You know what it is? This is what is called the focus. You know, an ellipse has got two foci. Okay? Now in one focus, there is one atom. Now, interestingly, what you see is that, you know, this is the spectrum which you see in the scanning tunneling. And you know, according to a simple geometry which we have read in our school, that if you allow a particular wave to get reflected from here to here, it will go to the next focus. So if you come from here, it will go. From here, it will go. So from here, whatever waves are emanated, it will go and converge to the next focus, and vice versa. Now, look, what happens is that these are the peaks corresponding to the atoms, and for this one, there is a peak. Now, there is no atom here, but still there is a peak here. What does it mean? This is a de Broglie wave, you know, which, the existence of the matter wave, you know, is something which is proved here unambiguously, that how come that there is a mirage peak which is seen here, even though there is no atom here. So this is called a phantom atom. So there is a real atom here and there is a phantom atom here, even though the atom in reality you have not put, but quantum mechanics tells us that look, if you start emanating waves from one focus, in the other focus there will be one peak, and that's exactly what you are seeing, thanks to the advent of scanning tunneling microscopy, and an absolute direct proof that quantum mechanics is not false. I have a doubt whether I'll be able to go through the entire details of my talk. The reason is that the time is not there, but I can at least mention to you a few things, and if anybody is interested in further details, we can discuss, separately. You see, there is something called EPR paradox, okay? Einstein-Podolsky-Rosen paradox, which is at the heart of understanding quantum information and entanglement that you are listening from the morning, okay? So, quantum mechanics makes several revolutionary claims about the fundamental behavior of particles. So, the claims are the particle acts like waves and particles interfere with themselves. Particles do whatever they want. There is a non-zero probability of finding a particle essentially anywhere in the universe, and measurement is inherently probabilistic. Now, Einstein was really shocked by these claims and he was convinced that quantum mechanics must not be correct. In fact, I'll show you soon that he had a lot of debate with Niels Bohr, and I'm coming to that. Okay. So, the EPR experiment, which is very well described in the literature, and this paper in 1935, it came, the Einstein-Podolsky-Rosen, can quantum mechanical description of physical reality be considered complete? Now, this paper, in fact, started a series of discussions amongst the people who were bothered about the logical foundation of quantum mechanics. I will skip this part and come to something which I thought is, so the formalism is not the whole story. The formalism of quantum mechanics is something means that what is the meaning of the state vector? Are state vectors the ultimate representation of the system? Is Schrödinger evolution universal? And why measurement processes are the way they are, okay? So, obviously the predictions of experimental results are all there. So, that is where ultimately we are led to what is known as the interpretations of the quantum mechanics. And that's the last few minutes I will spend, and I will stop. Now, this is something which I must confess that it is somewhat difficult for me to comprehend fully, but I know that historically it is the first one, that is the Copenhagen interpretation, the first one, which is most prominent. But after that, there were many other suggestions which have been given, because these interpretations are not unique. People tried to question the Copenhagen interpretation, and so there were other alternatives like de Broglie-Bohm interpretation, many worlds interpretations, quantum decoherence interpretation, consistent histories interpretation, and so on and so forth. It is not possible for me to tell you all the details, but at least one I can tell you what it means. Achha. Now, before I come to this interpretation, I will tell you this cultural clash. The interpretation, the people who are involved with quantum, the interpretations of quantum mechanics, there is a clash of basically people who are more mathematically oriented and people who are more physically oriented. Difficulty was the following: the mathematicians are more and more interested in abstract issues which are sometimes irrelevant for our lives, whereas the physicists, they became more and more pragmatic, caring more about applications rather than understanding. So, but you need both. The need of a precise formulation of the foundational issues is not taken serious enough by either of the communities, and that is why you can see so many interpretations which came. And the price one has to pay are paradoxes and philosophical implications. That is what is the price that you pay. Now, this is something which is very famous, and this is called the Bohr-Einstein debate, when the two champions meet, and this I read from this book by Abraham Pius, subtle is the Lord, but malicious he is not. That is the translation. The original quote of Einstein was, Raffiniert ist der Herrgott, aber boshaft ist er nicht. That is the original German, which was translated by Abraham Pius. Yeah, Raffiniert ist der Herrgott, aber boshaft ist er nicht. And here, this is a letter which Niels Bohr wrote to Einstein. It is available in the literature, in the Google. But what I'm going to tell you is something what struck me. I'm just reading these two lines here, what he said. He said that there are two kinds of truth. Here I'm coming to philosophy. There are two kinds of truth. To the one kind, the statements are simple and clear in such a way that the opposite of that is called false. But then he said there is other kind which is called deep truths. For a deep truth, there are statements in which the opposite is also containing a deep truth. So he says that I do not agree with you, he told Einstein, but we both are talking about something which is deep truth. So I am correct from my point of view, you are also correct. So it is not that the opposite of me is wrong. So something which is absolutely fascinating, you should read this letter from Niels Bohr to Einstein. I don't want to go into that. So this is the last one which I am going to tell you, namely the Copenhagen interpretation, which is the orthodox interpretation. And it basically says that the wave packet reduction is a measurement that is every measurement induces a discontinuous change in the state vector. The necessity of classical concepts in order to describe quantum phenomena, including measurements. And there exists a border which is called a Heisenberg cut between quantum and classical. Now, many of you have not understood what it means, so I have just made it somewhat simpler by telling you the basic principles of Copenhagen interpretation. A system is completely described by a wave function, representing the state of the system, as Schrödinger said. The description of nature is essentially probabilistic, and the probability of a given outcome of a measurement is given by the square of the modulus of the wave function. That is what is called Born rule. It is not possible to know the value of all the properties of the system at the same time. Those properties that are not known exactly must be described by probabilities. This is the Heisenberg's uncertainty principle. Matter exhibits a wave-particle duality. An experiment can show that the particle-like property of matter or the wave-like property in some experiments, both of these complementarity viewpoints must be invoked to explain the results. This complementarity principle of Niels Bohr. And measuring devices are essentially classical devices and measure only classical properties. And finally, the quantum mechanical description of large systems will closely approximate the classical description. This is the correspondence principle of Bohr and Heisenberg. So these are the ingredients of what is known as the Copenhagen interpretation. I think there are other interpretations also, but I will skip that excepting to tell you the names. The names are, for example, it is called the de Broglie-Bohm interpretation. De Broglie in 1926 came up with an interpretation, but later on he withdrew it after talking to Wolfgang Pauli. But then later on the same thing was reformulated by David Bohm, and it is called the Bohmian mechanics. I do not want to go into this. The third interpretation is the many world interpretation, which was given by Everett in 1957. It is called also the many worlds or many minds interpretation. And then there are various ramifications of this, which I will skip. And so basically this is the list. So Copenhagen interpretation, which came in 1920s and 30s. De Broglie-Bohm interpretation, which came in 1926 and reformulated in 1952. Many worlds interpretation, Everett in 1957. Modal interpretation in 1973. Physical collapse model 1976, and consistent histories interpretation in 1984. You see, look at why it was so many interpretations, because of the fact that none of these interpretations were considered to be something which is valid. So this is where the so-called lacuna of quantum physics comes. Okay, so I think I will close this by making only one comment. Quo vadis consciousness? In this context, I would just like to make one statement. We have done Maxwell's equations, which is a 4 first-order equations, but it can be coupled together to give 2 second-order differential equations in E and H, which is electric field and magnetic field. Now, a second-order differential equation has got 2 solutions. We call it retarded potential solution and advanced potential solution. Now, what happens is that we accept the first one, retarded potential solution. You go to any book, you will find out of the 2 solutions, you accept the retarded potential solution, you reject the advanced potential solution based on what? Based on causality. Now, what is causality? In the simplest possible way, if the cause happens at time t equal to 0, the effect can happen at time t greater than 0, which is common sense. If the cause happens at time t equal to 0, the effect can happen at time t greater than 0. That is the first one. Retarded potential solution obeys that causality. The next one, the advanced potential solution, says that if the cause happens at time t equal to 0, the effect can happen at a time t less than 0. Now, this is something which is against causality. So, the causality is something which dictated the second solution to be rejected. Now, the people who are bothered or bothering themselves about the relationship of quantum mechanics and causality, I think they deal with both these solutions, and I am sure you will listen more in course of the talks that you will see you will listen to in these 2 days. So I stop here today, but before stopping, I can't help you telling about today when we open a computer. All of you are opening a computer and you get huge amount of data. I know that you are aware that all these data, most of this data is junk, okay? Because from this data, if you want to get the information, you have to really go with a magnifying glass. So all that is data is not information. So you have to really go into it and get information from the data. This is so huge data, this much of information. I continue. All that is information does not necessarily lead to knowledge. You get information, fine, but that does not necessarily lead to knowledge. All that is knowledge does not necessarily lead to wisdom. There is a difference between a knowledgeable man and a wise man, okay? Wisdom is different from knowledge. So all that is knowledge is not necessarily leading to wisdom. And all that is wisdom does not necessarily lead to truth. So why I said that is that in our Indian philosophy, we have seen so many saints, such as, Ramakrishna Paramahansa. Obviously, Ramakrishna Paramahansa Dev did not use data, information, nothing. But whatever he told is something which is truth. So, he short-circuited the entire thing and came directly to what is truth. With that, thank you very much.
A beautiful presentation, and I think it is just the best starting point of this conference, because now we have heard about quantum mechanics. The next progression will be quantum consciousness or quantum mechanics and consciousness, and later on we will have consciousness. So what can we ask for? It's really fantastic, exciting start, and I will request the whole audience to give a grand applause to both of the speakers of this session. And there is a question-answer session after this. If anybody of you has any questions, queries, not inputs, questions and queries, you may have your own theories that can be discussed over lunch. But what I am asking you is specific questions and queries on the subject area that was discussed, spoken on. That is, please don't ask questions on, say, India's cricket team on this particular session. So basically, if you have any questions, they are all welcomed. Yeah, I think there is one person over there. Yeah, just wait for, I think the mic will go.
My question is to Professor Das. Firstly, Wundaba, the cobalt and copper experiment that Professor you just showed, on the second focus, we see the intensities. I could roughly make out it's approximately 1/3 of the intensity at the first focus.
Yeah.
So could you explain why there's such a difference between the intensities?
Yeah, very, very good question and observation. I appreciate that. Yeah, the reason is that when you superpose the different matter waves, let us say, which are going, now it depends on how the amplitudes of those are adding together. Now, unfortunately, all the amplitudes do not add vectorially. I mean, do not add just like that. It adds vectorially. When you add two vectors, A and B, it need not be just the sum of modulus of A and modulus of B. It need not be. So vector A plus vector B need not be the same as the modulus of A vector and modulus of B vector. So your observation is absolutely right, that it is 1/3 almost. But that's not what I wanted to say. I wanted to say that, look, the very fact that there is a peak out there when there is no atom out there, that shows that unless there would have been the so-called, the so-called matter waves, yes, you would not have seen anything out, yes, there, right? So, but your observation is absolutely right, and that is because of the fact that the amplitudes, they add vectorially and not just like a scalar.
Okay. Vielen Dank.
Thank you. Yeah.
Yes. Okay.
I think there are people here who are so much more knowledgeable than me. See, the point is that, ultimately we do science or we do religion, even though the latter one I cannot comment so much. But why we are doing that? We are doing this because ultimately we are trying to aim for the truth. Yes. Now, for that, we see a lot of wisdom amongst many of us, many people. Okay. Now, are all the wisdom leading to the truth? The answer is not. What I am saying is that truth is a subset of the wisdom. Wisdom is a subset of knowledge. Knowledge is a subset of information, and information is a subset of data.
Yeah, just sir.
You have mentioned in your slides that Einstein did some statistical analysis based on which he had that recapitulate the Planck's. What statistical analysis Einstein have done?
Oh, well, when I said that there is a little bit of inaccuracy, what I should have said is did a statistical mechanical analysis.
Okay.
That is, he used statistical mechanics, which he himself formulated actually,
Yeah.
independent of Gibbs. And through that statistical mechanical analysis, he drew the conclusion that there were two terms he got, one which is characteristic of particles, the other one characteristic of waves.
Yeah, thank you.
I'd like to ask one basic question about the wave-particle duality. Is that whether the wave converts into a particle or the wave behaves like a particle, or they both exist simultaneously? Whether the wave and particle, they exist simultaneously, or the wave becomes the particle, or the wave doesn't exist at all and becomes a particle. What really happens?
So this is actually where the interpretation comes in. There are various interpretations. In the standard version, which is the Copenhagen interpretation, as Professor Das was saying, the wave, the psi function, is what is called a probability amplitude. when you take its, you multiply it by its complex conjugate, you get the square of it, as it were, then that gives you the probability of finding a particle. So the wave function is something like this. It gives you the probability amplitude of finding a particle at some position x at some time t, if you were to make an observation on it. Now there is another interpretation which he talked about, which is the de Broglie-Bohm interpretation, in which the particle and the waves exist at the same time, in the sense the wave is called a pilot wave which guides the particles. So in that sense you have particles, waves and particles, whereas in the Copenhagen interpretation you have either waves or particles.
And then another question is that can the same wave behave like different particles? Is it possible?
Same
the
wave?
Same wave is
okay. So okay.
Having the
one of the fundamental
characters of different kinds of particles, say oxygen, hydrogen, or like that, or
no,
photon.
They will have. If you have different, hydrogen has a different wave function from an electron.
Okay.
Sure. Completely different wave function. And also the wave function, in the standard interpretation, the wave function has a single particle interpretation. That is, it is the wave function for a single particle. Now, whatever that means depends on your interpretation.
Can there be any wave without having particle?
Empty waves.
Waves without particle, can
That's
there?
what I'm, empty waves.
Yes.
Well, this has been speculated, but there is no empirical evidence so far for it.
I mean, just to tell you that, you know, Maxwell's original theory, which tells us everything about the different kinds of waves that every time we are experiencing. Like, for example, microwave, radio wave, everything is a wave. Radio wave, which is we are using, microwave we are using in our kitchen, X-ray we are using when we go to hospital, blah blah. Everything is a wave. So now there, even if you do not go into the particle picture, the waves are there. I mean,
they are classical.
They are classical. So I mean, without that you cannot. That is the reality. But what we are talking about is for example, de Broglie's concept, which both of us talked about. So it's a matter wave. Now, matter wave is something whose wavelength lambda is inversely proportional to its momentum or velocity. So lambda is proportional to 1 divided by p. What does it mean? That means if the momentum is very high, then the lambda will be very less. And lambda will be very less means the energy will be very high. So you can see it. Now suppose the momentum is very small, p. Let's say the momentum of a train. Now that is something, or a person who is running. Now the person who is running you can consider it as a particle. Question is there a wave associated with it? The answer is yes, it exists, but you cannot see it. Why? Because the lambda, which is proportional to 1 divided by p, is so small, the lambda will be so large, you can't see it. That's it.
Yeah, so the question, I suppose, was about quantum waves, not classical waves. Classical waves are waves which have no particles in them. But quantum waves always have some particle associated with it, because that is the wave function for the particle.
I have a question to Dr. G.P. Das. My name is also G.P. Das.
He is a very famous, quantum chemist of the world. So I am very happy that you are here.
Oh, thank you. Thank you.
Guruda, why don't you yeah. So Professor Gurupada Das from United States, I mean, we are very happy that he happens to be here. I mean, he has spent almost his whole life in the field of atomic, molecular and quantum chemistry physics. So,
thank
yes.
you. The question that I have is relates to this version of causality that you have mentioned. Yeah. Now, I might be mistaken. Or maybe both both meanings are probably accepted. There is another type of causality which actually refers to the principle that there is an effect. The effect and cause are they're related. There is a one-to-one correspondence between cause and effect. That means if there is a cause, there is a corresponding effect. If there is no cause, there is no effect. Is this also one of the meanings of causality? Because this is very important for the discussion on consciousness.
You are absolutely right.
Yes, I mean,
yeah.
Is it something that is accepted in the jargon of physics, or it's more or less?
Well, I do not know whether it is very well accepted in the jargon of physics, but the people who are talking about the relationship of quantum physics with consciousness, they are invariably talking about the causality.
Particular meaning
the one which you are talking. Professor Das, what I mentioned is simply the following. You have got a second order differential equation.
Yes.
It has to have two solutions.
Yes.
You can't help it.
Yes.
Why the hell are you throwing away one solution? You are throwing away the advanced potential solution. This is in every book. It is there. And we are only taking the retarded potential solution for the electric and the magnetic field.
By the way, it is true only for Schrodinger equation.
Klein-Gordon.
No, I'm sorry. It's Klein-Gordon or Maxwell's equation, but not for Schrodinger equation.
No. Yeah, you're right. Thank you. Yeah. Oh, yes. There is a...
Since energy can be quantized, can we assign a temperature to vacuum or at least specify an energy state for vacuum?
Okay, so let me see if I can answer this question. See, first of all, energy and temperature, they have been related in the most famous way by Boltzmann. That is, E is equal to Boltzmann constant multiplied by capital T, which is the temperature in absolute scale. 273 degree is a minus 273. You have to add 273. So, energy, or in other words, there are so many molecules in this room. There are nitrogen and oxygen molecules in this room. Huge number, 10 to the power some 30 or whatever. Now, all these molecules are bumping, which you can't see it in your eyes. But today, all that you can see, how many times these molecules are bumping along each other, you can't see it. But that will dictate what is the net energy of the molecules in this room. And how do you know what is the energy? No way to know, excepting that you put a thermometer here and see the temperature of this room is, let us say, 24 degrees centigrade. And that temperature is related to the energy of the scattering of all the molecules in this room. Now you put the AC on, more AC, you start freezing. What happens is that all these molecules, they are still bumping with each other, but in a different way. Total energy of the molecules in this room, which comes out because of this scattering, is different from the earlier case when the AC is on. But the only way you can see is by temperature. Take a thermometer and see the temperature. And that is the beauty of thermodynamics. Thermodynamics is related to microscopic world, which is called statistical mechanics or quantum mechanics. Whether this comment I would like to make, and Professor Ghosh will be... See, quantum mechanics you can question. Thermodynamics you cannot question. Am I right? Thermodynamics you cannot question. You cannot question thermodynamics. Thermodynamics is something which is applicable to subatomic world, to the cosmos, everywhere. It is applicable, okay? Because it is a macroscopic property which can be explained by means of microscopic roots. So, but then you had something else at the end of your...
Sir, can we assign a temperature to vacuum?
Vacuum. So, now, okay. I think, See, let me see. I mean, I'm not a cosmologist. But the point is, the cosmologists have given a tremendous amount of thought about the whole thing, and they do assign some temperature. For example, cosmic background radiation. I think he's the best person to talk.
First of all, according to the present understanding, there is nothing called a total vacuum, right? Generally, we say vacuum is a space where there is nothing, but there is nothing called nothing, because even if there is no matter, it can be a energy field. For example, in the space, as he has just mentioned, we said there is hardly any object, so most of the space is vacuum. But we know, starting from, professed in 1948, and starting from 1965, scientists have found out that space itself has a basic temperature of roughly 2.73 Kelvin, which is minus 270 roughly degrees centigrade. So you cannot, in the classical sense, you cannot call it that there is a vacuum, first of all that. Secondly, nowadays you regularly hear terminologies as dark energy, vacuum energy, and 70% of our universe is dark energy or vacuum energy. So what does it mean physically? I really do not know deeply what does it mean, because I do not know any scientist who have given a clear-cut definition of vacuum energy. But basically, in common layman's term, they say that every point in space can give rise to, birth to, generate particles, right? A particle and an antiparticle. And they can again come together, annihilate each other, and produce the same energy. So energy to matter, matter to energy is continuously going on at every point in space. In case of an electron and a positron, this thing happens, generation and annihilation, at a scale of 10 to the power minus 21 second. In case of a proton-antiproton, it can happen at a scale of 10 to the power minus 26 seconds. What does it mean? I do not know in terms of smallness. But we know that there is no physical instrument which can measure an event within that short time scale. That's why they are called virtual particles. That's why we talk about virtual pair productions. And that happens because of this sea of energy, or an energy field that is there. So, first of all, our classical definition of vacuum is going through a sea change. What we used to call vacuum, is it there a true vacuum? One. And second, vacuum can be thought about as a phase, which can, like a phase transition, you can go through transition from a vacuum to another stage. And in terms of energy, vacuum energy, there are new concept of this pair production, but virtual particles, and much more detail, which I'm not going into, in terms of symmetry and supersymmetric consideration.
Temperature, that's what he says.
Temperature, yes. As we know vacuum in the universe, yes, you can, as a cosmic microwave background radiation, which has a temperature of roughly 2.73 Kelvin. That's it. But that is radiation, that's why inherent definition of vacuum is so difficult. It's almost ununderstandable. So that doesn't question. Unless or until you have a physical entity, you put a temperature or some properties on it. Right? But our classical way of looking at vacuum is there is nothing. But that is not the case. That's why I'm saying.
We can discuss it more.
Right. So it's a very complicated, but a very good question actually. That much I encourage. It's an absolutely good question.
Sir, just for, sir.
Yes, cosmological constant, vacuum energy, they are somewhere getting mixed up, repulsive and all sorts of things. So I'm not going into all the details to this basic question.
And sir, like as you mentioned, like there, all around, all throughout the universe, if there is this sea of virtual particles or quanta, as you mentioned, they themselves have their own energy. Like, as you mentioned, our concept of vacuum is not clear right now, but these small particles, this entire sea of particles which is there throughout the universe, all of them have their own energy, and they are associated with something that is in motion or maybe at rest, like with reference to one particular observer.
Right.
So, since they are related to these other particles which are in motion or at rest, is it possible that when we are exerting an external force on it, these particles will try to oppose that force?
I think no.
I mean-
I don't think. Okay.
I don't think so.
No, let me tell you, this is the basic idea of quantum electrodynamics, which is quantum field theory, is that in the vacuum, you can't, as he said, you get continuously particle-antiparticle pairs coming up and dissolving. Okay? Within such a short time that you have this uncertainty principle, the uncertainty in energy multiplied by the uncertainty in time is greater than or equal to some Planck's constant, right? So within that time, the energy conservation law does not hold. But it's called, these particles are called virtual because they'll never come out as real particles because they don't have sufficient energy to come out. But the theory is that everything is full of these, the creation of, continuous creation of particles and antiparticles, and it's very complex, messy thing.
Like, okay, so
just a minute. However, supposing you could, so every electron is surrounded by what is called a virtual cloud of electrons, positrons, and photons, which are continuously coming out and dissolving. So a real electron is not what is called a bare electron. It is a dressed electron, which is surrounded by a cloud of virtual particles. And that's what you see. However, suppose you kick that electron, give it an acceleration, then you have supplied energy to it, so these virtual particles can come out as real particles. And that's exactly what happens in the antenna. When you accelerate the electrons in an antenna, they give out electromagnetic waves. So the quantum theory version of that is just this. As you said, you give it an acceleration, then you impart energy to the system, and that energy can be converted by Einstein's equal to mc square into particles which can fly out.
Yeah, a very good question, and I will request you that if you have any further queries, you can definitely contact one of our speakers over here, and they will be very happy to make you understand to their level what they want to say. Any more further questions? One here, then I'll go over there, then there. Yeah.
Yeah, my question is to Dr. Partho Ghosh. How do you classify a particle, whether it's a bosons or fermions?
Well, that's a very good question. I didn't have time to go into all these details, but thanks for asking me. Well, nowadays we have a theorem which is called the spin statistics theorem, which says, you know, every particle has a spin. That is something like a spinning top, but that is a rough idea, huh? Because the particle is a point, so there's no axis, so it cannot spin in the usual sense of a top. But there is some angular momentum associated with particles. It can have a zero value. But in quantum theory, its values are quantized. That is, it can be zero, or it can be 1 unit of Planck's constant, or 2 units of Planck's constant, or 3 units of Planck's constant. These particles are invariably bosons. But you can also have half unit of that, or 3 by 2 times Planck's constant, or 5 by 2 times Planck's constant. These are called spin half, spin 3 by 2, etc. particles. These are all fermions. So that's the difference between bosons and fermions. And another difference between them is that you can pack as many bosons as you like into one quantum state. But fermions have this property which you mentioned of the exclusion principle. That is, you cannot put more than one fermion in one state. So these are the differences.
I think next question. No, I think somebody from here is okay? Okay, next question.
Sir, so my question is mainly from the experimental point of view. So like whenever we do some experiments, we use some probes to measure the state of a system. Maybe say magnetic field or electric field or anything. So when we are doing such measurements, then we are actually trying to perturb the system and then we are disturbing the system. So in some sense, we are actually not, so is it true that we are actually not measuring the actual system, the real system which we would like to measure? So we are just seeing the manifestation of the system. So how do we resolve this?
You are right. Yeah.
Well, this is a good question. The point is this. In classical physics also, you can say that when you measure something, you are disturbing it. But the theoretical construct is such that you can minimize or you can make that disturbance as small as you like. Within the theory, there is no inbuilt cutoff. So actually, if you are a good experimenter, then you will know how to minimize the disturbance that you are causing. That's your skill. But quantum physics says there is a definite minimum to the energy, to the disturbance that you can cause. That is what causes all the problems.
I think there are a huge number of people who are going to ask questions. I'll take, don't worry, but one consideration. The food that has been prepared is almost at the ground state now. Energy gone, temperature very low. So we should limit our question. I will take two more questions, one from here and next as yeah, please.
Yes. Give the, just take the microphone. Yeah.
So you were talking something about Maxwell equation, second order differential equation in magnetic field and electric field. In that case, you considered two solutions, retarded potential and another one was advanced potential solution.
Yes.
And then you mentioned the discardation of the second one due to the failure of the causality,
Yeah.
Which was like cause if it's in T1, then the effect has to be T1 more than 0 if that is in T1.
Correct.
So, sir, my question is that if I assume that electric field is my cause, which I am saying, so the very fact that I am assigning cause to electric field depends upon my observation. So, sir, what if I change my motive and I say not start with cause, I start with the effect, and then, sir, the very fact that if effect is at t is equals to 0, then cause can be at t at less than 0 will certainly start making sense in that case. Okay. Because it just depends upon my perception, how I see as a cause and an effect. Because each thing which is a cause can be an effect and an effect of something back in time and forward in time.
It's a question of semantics. Yes, I agree. Yeah, I agree with you. I mean, yes. I mean, the cause and effect, in which way you did defining it, it depends on that. But it needs a little bit more discussion. It requires more discussion.
Okay.
I'll just like to make one point. You know, one must distinguish between causality and determinism. The two are not the same. Whole of physics is deterministic. That is, given the state of a system at one point, you can either predict or retrograde. You can go because all equations of motion are time reversal invariant. There's not a single equation which is not so. Of course, we know that weak interactions may violate this, but apart from that, so this world is deterministic. Now, when you bring in the concept of causality, you are bringing in something else also with it, where the sequence is important. What you call a cause must, by definition, precede the effect. Otherwise, you are using your words without understanding what they mean. But determinism, you can go both ways.
Next.
I think the last question from this young participant.
Sir, I would like to ask this question that, we are having so many interpretations in quantum mechanics, we are having so many difficulties also. And Richard Feynman also says that nobody understands quantum mechanics. He says it safely. I mean, my question might be a little bit outrageous to the mathematicians here, but I just want to ask that, are these difficulties arising in quantum mechanics due to this inefficiency of mathematics being used as a tool in investigating the reality which we see around us?
I mean, it may vary from person to person. I don't think so. You see, mathematics is something which is used as a tool. Let me just tell you one thing. I mean, the fact that, E and pi both are transcendental numbers, E. E, exponential, E, pi. They are transcendental numbers which are non-terminating, non-recurring decimals. Okay? So you cannot express E and pi as in the form of P divided by Q. You cannot do that. So these are called transcendental numbers. But lo and behold, there is a relationship which is e to the power I pi is equal to -1. And that is something which the great man Laplace had told. Unbelievable. I mean, this is exact relationship. So mathematics, I gave you that example because this is exact. I can't blame it to mathematics. See, Dirac, when he found out his positron, which he mentioned, he found out first from mathematics and then tried to explain. Of course, Bohr's idea was different. I don't think that you can blame mathematics for that. Maybe Professor Ghosh, you have something.
No, I have a slightly different take on this. I completely agree with what you have said, but there is another angle. Maybe that is what this young gentleman had in mind, which is what Einstein had in mind, which is the current mathematical formulation of quantum mechanics complete? Or is there a way of formulating it with another kind of mathematics in which all these problems will disappear? The answer is we do not know yet.
And the so-called deficiency you are mentioning, thank God it's there. Otherwise, science would not have progressed. We'd have learned everything by now. Right. Okay, I thank profusely both the speakers of this session. And one amazing thing both of us mentioned to me that I should mention is the rapt attention and the intensity of the participants. Absolute beauty. I have hardly come across any conference which for almost 2 hours has captivated the audience, definitely by the oratory power, but also by the integrity of the participants. Thank you very much for coming here today. And I think it's a great beginning, and it will go on in a much, much better way, in a bigger way, and it will end in a fantastic conclusion, I hope. Thank you very much. Lunch.
Hello. We have some small mementos to present to our speakers. May request Professor Duwari to please present the mementos to Professor Ghosh and Professor Das. Please be seated.
I think we will best applaud our speakers by being present here when the organizers are presenting them with a small token of appreciation. Just.
Yeah, please. Now I will request Professor Sujito Ghosh to please come on stage and give mementos to our session chair, Professor D.P. Duwari. Big round of applause. There is a small announcement that we have reduced our lunch time for nearly 40 minutes only from right now. And we have outsourced exhibition and our bookstore also. You can go there and visit during that time. So we will again meet here in our next conference. Please maintain time. You see that kind of discussion and lectures. We are very excited. So it's 3:30. Okay, so we will be here at 3, possibly by 3:30. Okay. Thank you.